Hello, hungry learners. Welcome to another Storytelling Science Lab video. Today we'll be discussing fictional materials, including the Poisson ratio, crystal structure, the difference between hardness, strength, brittleness, ductility, and chemical resistance, as well as an overview of some options you have when you are designing your own fictional material and what to consider, some details about alloys. A lot of fun stuff planned for this video. Without further ado, enjoy. The Poisson ratio. The Poisson ratio is determined by how much a material's cross-section thins when it is strained perpendicular to the cross-section being observed. Most materials will thin by an amount that's closely correlated to the amount of strain that is being applied, but some materials are different. For example, a material with a Poisson ratio of exactly 1 will thin at exactly the same rate as it's stretched. A Poisson ratio of 0 will mean that it can be stretched or compressed, and the cross-section perpendicular will not change at all. Most materials, almost all materials, are between these two. A Poisson ratio of -1 means that the cross-section expands as the strain is applied. This mostly happens when you have it was a children's toy that I was unable to find the name of, but you pull on any side of it and the whole ball expands. It's like that. So it's possible for there to be chemical structures that are like that expand, but that would mean it expands to a point, and then if it's stressed further than that, then it begins to thin just like any other material. A Poisson ratio of greater than 1 means that it gets thinner faster than it's stretched. But again, most materials, it's closely correlated. You can't get material from nowhere. So when it's stretched, the material flows from the region being strained to stretch it and make it longer. I have a model that I've made to help you understand this. Crystal structure. Crystal structure is how the atoms of a given material organize themselves. Some materials have cubic crystal structure. Some materials have no crystal structure at all. Most solids have a crystal structure. Any solid that doesn't have a crystal structure is called amorphous. Most gases don't have a crystal structure, but some liquids do. Water tends to organize itself into a loose crystal structure where there's sheets that sort of slide on top of each other. This creates water's surface tension. I'll do a detailed analysis of all crystal structures in a future video. Fun fact, crystal glass. Glass by definition is an amorphous solid. Crystal by definition has a crystal structure. Crystal glass, also known as lead glass, has no crystal structure, and so the name crystal glass is just kind of an oxymoron. I've made another visual aid to visualize impurities in the crystal structure. Hardness, strength, ductility, brittleness, and chemical resistance. Hardness is a material's ability to resist plastic deformation. When strain is applied to a bar, the bar bends by an amount that is corresponding to the force essentially divided by the strength of the material. I'll get into strength later. But if a bar is bent this much and it's able to return back to its original shape, we'll say that this is the maximum amount that the bar can be bent before the hardness is overcome and the plastic deformation occurs. So if you bend this bar by a little bit more, if you bend it by that much, you see it's able to resist this. It would be able to resist that, but now you see it's gone all the way. So you've bent it by this much plus this much. So the bar would return to the total amount minus the amount it's able to resist. And so that's why sometimes when you bend something and it plastically deforms, but it springs back up some, but it doesn't spring back all the way, and it also doesn't just stay exactly where you put it. If it has a hardness, it will deform by the amount you deformed it minus the amount that the hardness would be able to resist deformation. This, of course, is a overly simplistic way of viewing it, and there's many calculations involved, but at a basic level, this is how hardness works. It resists plastic deformation and will spring back to the original shape if its hardness is not overcome. Hello, Hungry Learners. I was not originally intending to make this video a two-part video, but both of my video editors have not been able to edit for me, so I've been doing it myself, and it just takes a long time. So I decided to cut this video here and just go ahead and get it out for you, and part 2 will be coming out at some point in the next month. So I hope you have a good Thanksgiving, everybody. Thank you for your support, and I'll see you in the next one. Thank you for watching this video. To keep Storytelling Science Lab free, please consider a small donation at our Patreon, Storytelling Science Lab. Be sure to like and subscribe. Comment, letting me know anything that you found outrageous or offensive in the video. I'd love to hear your thoughts down in the comments. Thank you to our patron, Saluma, for supporting us. As always, any donation is much appreciated. I'm developing a board game called Drone Control, which the details for will be on our Patreon very shortly for free, as well as downloadable free printouts for the game pieces. Have a great day. Thanks for watching. And as always, stay hungry.